This 6 just automatically, the coefficient of the dividend automatically becomes the first coefficient of the quotient, right?
Yeah.
And that relies on the fact that you're dividing through by things with the form x minus a. All right, so before I even do anything, I can just straight up tell you that the first coefficient of the quotient is going to be 6, yeah?
Yeah.
Okay, so we just bring that 6 down. All right, what was the next step of Gauss polynomial long division? It was to multiply 6 by -4, right? And then write that there. And then subtract. Well, instead of multiplying 6 by -4 and then subtracting it, why don't I just multiply 6 by +4 and add it? That is the exact same process, right? And when I do that, I get 3. Boom. Oh, and by the way, conveniently, what was the next step of the algorithm? That thing you get from subtracting just automatically becomes the next coefficient in the quotient, yeah? And I've already just dropped it into the spot right there, like there it is. We're writing the quotient as we go. Okay, and then, what was the next step in the algorithm of Gauss polynomial? We'd take that 3, we'd multiply by -4, get -12, and then subtract that -12. Well, instead of multiplying 3 by -4 and subtracting it from -13, we could just multiply 3 by +4 and add it to -13. Cool?
Cool.
Boom. We get the -1, which automatically gets sent up to be the next coefficient of the quotient. And then finally, okay, we do it one more time, right? -1 times -4 is 4, and then we subtract it from -6, but this time we just multiply -1 by +4 and add it to -6. Boom. And that last number at the end is your remainder. Boom. All right, synthetic division is really, really fast. And this is why people like it. It's very, very quick, efficient, takes up very little space, but it just is polynomial long division, like literally in a via a step-by-step examination of the algorithm. Okay, good. You're one of the like 0.1% of Americans who understand why synthetic division works now. And it only works this is only relevant in the case when you're dividing by things with the form x minus a. All right, so to summarize, where are we right now? So here's what we've done. We did this thing. We did 6x cubed minus 21x squared minus 13x minus 6 all over x minus 4. And we concluded that this was 6x squared plus 3x minus 1 minus 10 over x minus 4. And then I would like to encourage us to sort of rewrite this as an equivalent statement, 6x cubed minus 21x squared minus 13x minus 6. That cubic actually just is 6x squared plus 3x minus 1 times x minus 4 minus 10. Okay. So that's kind of like what we did, right? Well, now thinking of this original thing as like a function, the dividend, let's call it f. There's something I notice if I plug in 4. What is f of 4? Yeah, if you plug in 4, then you just get -10, right? Immediately. Because, right? You just get -10. Okay, and so that's kind of cool. Actually, this has a name. This thing that just happened. This is called the Remainder Theorem. And the Remainder Theorem says that if you divide a polynomial, I'm going to write this down in a minute. If you divide a polynomial by x minus 4, then the remainder that you get is just the value of that function when you plug in 4. Okay, let's kind of just like do it in general, and then I'll write down that sentence. So here we go. Take a function, a polynomial function, and divide that polynomial function by something of the form x minus k. All right, if I do that, then I'm going to get some kind of quotient, right? Okay, so here is my quotient, and I'm going to have a remainder. What can I say about that remainder, by the way? it's the degree of that remainder has to be less than the degree of the divisor, which is 1, right? So the remainder has to be just like a number. Okay, so it's always going to look like this. Okay, if this were higher power, then you could keep dividing. Okay, so this is kind of what happens when you divide.
It's q of x times the divisor.
Oh, no, not yet, because I haven't. First, I took a polynomial. I think I've done this right. I took a polynomial, divide by x minus k. I get a quotient plus the remainder. Right. The remainder of x again. What you're saying is what I'm about to do, which is to say that another way of thinking about this is to say that f of x is q of x times x minus k plus r. Cool?
Yeah.
Okay, cool. And now we get to state the remainder theorem. The remainder theorem says, and now we'll just do one quick thing, which is to plug in k. If you plug in k, once you've rewritten the function in this form, then if you plug in k, what do you get? R. And so the remainder theorem in words is just this observation. The remainder theorem says that the remainder after dividing polynomial f of x by x minus k, the remainder that you get just is f of k. I think I said that right. Cool? Okay, the remainder theorem is like cute and stuff, but what's even better is the factor theorem. Alright, what is the factor theorem? The factor theorem is just the special case where this special case where r equals 0. If r equals 0, then what? Then x minus k, then just sort of divided through evenly, right? And so what the factor theorem says, the factor theorem is, remember the stuff, you guys did this kind of stuff last year, I think, with Kurt, right? You were given some cubic, like, I don't know, 4x cubed minus 2x squared plus like 5x minus 1. And the goal was to find all the roots of this polynomial. But like that's hard, because like it's hard. So then he would just give you a little thing. He'd be like, yo, I'll give you a little fact. Here's my little fact. F of 3 is 0. By the way, it isn't for this problem. But let's just say, suppose it works. Okay, now that f of 3 is 0, what you were really supposed to use at this point was knowledge of the factor theorem. Because the factor theorem says, oh, if I plug in 3 and I get a remainder of 0, then it must be the case that x minus 3 divided into that polynomial evenly. Yeah? And then you concluded from this that f must be in the form x minus 3 times like some stuff. And then you went and did polynomial long division to find the stuff. Alright, cool? Alright, good. That was the theoretical part of the lesson. The last little coda here is that because polynomial long division, because synthetic division is so efficient, it means that like just searching for roots is like not that time consuming. Alright, I got a function for you, and as soon as we find the roots of this function, we will leave. And here it is. It is a cubic. It does not seem to have any particular pattern. It does not seem to be factorable in any kind of way. So what we are going to do now is blindly guess what some roots might be. I have a good guess for you. 1. There is something called the law of ones. The law of ones says that 1 is often a root, because that would be nice if it were true, and so a lot of big problems have been written that way. Okay, how do we check to see if 1 is a root? Divide through by x minus 1, and see if we get 0. A remainder of 0, to see if it goes evenly. Okay, so you just throw up the coefficients, -3, 20, -36, 16, and you just stick a 1 here, and you just very quickly try it. It takes like 5 seconds.
-3, 17,
What did we find? It's not 0. That means teacher is cruel. Corollary of the law of ones is -1 is often a root.
I mean,
I'm just gonna.
-3, 27.
It doesn't seem to be working. Corollary number 2. 2 is often a root.
Wait a minute.
Okay, do you find this to be faintly ridiculous?
Yeah.
Okay, good. That means you're critical thinkers. Did it work?
Yeah.
It worked. Boom. Now we know that 2 is a root, which means that this function must look like x minus 2 times some stuff. And what is that stuff? It is specifically this polynomial, right? Because that's what synthetic division does. Synthetic division is not just checking to see if 2 is a root, it's also dividing by x minus 2, giving you the coefficients of the quotient polynomial at the same time. Get it? Okay, cool, goodbye.
Bye.
Goodbye to period 4.
I think a really satisfying way to take